So in the previous video, we've learned about the loss function, which can measure the difference between our prediction and the true label of the data. And it can tell us basically how good or how bad our current model with respect to the data instance that we would like to classify. However, we have not talked about how we may improve the weight and the bias term in the logistic regression. In this video, I'm going to talk about how we may start from a particular set of weights and the bias term in the logistic regression model, and then we're going to use a method called gradient descent to improve the weights and the bias term. Just a little bit of recap, our problem is a supervised learning problem, and then we would like to learn the set of weights W and the bias term B to make our prediction Y hat as close as possible to the true label Y. And then there are two things that we need to learn W and B. First is the loss function that we have discussed in the previous video. It will measure the distance between our prediction and the true label. And second, which we're going to talk about in this video, is the gradient descent method, which is useful for iteratively updating, so step by step, improving the weights and the bias term with the objective to minimize the loss function. So in other words, we're going to search for the better and the better W and B values such that the loss function will be get lower and lower. Okay, so let's start with this gradient descent. The basis of the gradient descent method is gradient. So let's take a look at an example. So here we suppose we have a function of 1 over 2 times x squared. So this is the function. And then do not be confused because here the x-axis is not located at y equals 0, but it's located a bit down there, but that shouldn't confuse you, okay? So here's the function of half x squared, and then let's take a look at this point. So let's say we're looking at the point x equals 1. So here we have the gradient at this point, which is positive. Okay, so the gradient of this function here is the gradient, or the first derivative is just x, right? So at the point of x equal 1, the gradient is positive 1, which means that if we increase the x, if we go to the right a little bit, then the function value will goes up. Okay, that's why the gradient is positive. Okay, actually this shift from x 1.0 to the right should be super small. Okay, it's almost 0. Okay. Now let's take a look at another point. Now we take a look at the point in the negative region. Okay, so we take a look at the point x equal minus 1. Here the gradient is negative 1, gradient negative 1, which means that, okay, it's not a very good line, but you get the point, which means that if we shift a little bit, increasing the x value from minus 1 to, let's say, minus 0.99999 and so on, we will get a lower value for this fx function. Okay, so that's why the gradient is negative, because if we increase the x value, then the function value will go down. And then at the point of x equals 0, the gradient is 0, because if we shift just very slightly a little bit, increasing the x, then the value of fx should not change. And if we look at this gradients here, so in the positive region, the gradients are positive. In the negative region, the gradient is also negative. So if we try to reach the minimum here, the minimum point, we may use the clue from the gradients. For example, here, since the gradient is positive, if we are going to reach the minimum, it means that we need to decrease the x value, right? But if the gradient is negative, which means that if we increase the x value, the function value will go down. It means that we need to increase the x value. Okay, so using the gradient, we know that, okay, if we go there, the function will go up. So if we want to minimize the function, we should go into this direction. Here in the negative region, we know that the gradient is negative. So if we want to minimize the function, we just follow the gradient. So that is the basis of gradient descent, such that we may improve our W to minimize the loss function. Here, let's take a look at another example. Suppose our current weight is here, W1, and the loss function is there. We see that the gradient is negative. So our new W would be the old W that we have currently minus the gradient, because the gradient itself is negative. It has the negative sign. So finally, our new W will be the old W plus some value of the gradient. Okay, in other words, our new W will be uh, somewhere around here, which is increasing from the old W. And then we see that the loss function value goes down. Suppose our W1 is here. This is the loss function value. We check the gradient, it is positive. We will improve this W negative to the gradient. Okay, so we will reduce the value of this gradient, and suppose the new value is here. You can see that the loss function goes down. Okay, so we are going to move according minus times the gradient. So here are the complete steps of learning W and B in logistic regression. The step one, as we have seen before, is that we define the loss function. So we say here our loss function, given the instance x, given the label for each instance, and then the set of parameters that we currently have. So the theta is the W and also the bias term. So given all these things, we can compute the loss function value, and then we take the average over the m instances in our data set. What we want to do is that we want to find the set of parameters. We want to find the W, we want to find the B, such that the loss function is minimized. Okay. And so that's the first step. We define the loss function, and then we calculate the loss function with respect to the W and B that we currently have. Now, the step two is that we perform the gradient descent, which that we take the current W, or it can be also the current bias term, and then we shift it with, or we change it with minus times the gradient. Okay, so this term is the gradient of the loss function, with respect to the parameter that we try to improve, for example, with respect to W. Okay, and this eta here is a constant. Usually this is small, like 0.1 or smaller than that. Okay, so here's the complete function, and then we go back here once we get the new W and also the new B, and then we calculate again the loss function. Calculate the loss function, and then if we are not satisfied with the loss function value, we do the gradient descent again, so we get the new W, the new B, and then we go back to step one, calculate the loss function again, and then we keep doing these two steps until we are satisfied with the loss function. We think that the loss is already small enough. So here's the loss function that we've seen before in the previous video. And then we do the gradient descent with respect to a single weight. And this is the gradient, okay, with respect to a particular W. So Wj here, let's say this is for W2. So this formula becomes sigma Wx plus b minus y times x2 because we're updating, for example, W2. And then so the complete update is that this is our old W minus the eta constant, let's say 0.1 times this gradient. And this gradient is given here, okay? And you see everything is already given, like X is the instance, it is given in the data set. Y, the label is also given. And then W is our current weights, which is also has the numbers. B is the current bias term. And then sigma is the sigmoid function. And then xj is the jth feature of our instance. So these all has the numbers, and this is the gradient here is already provided, so you may update the weight. So we are going to improve the W and the B based on the gradient. Specifically, it will be improved by minus times the gradient. But if we're looking at the gradient itself, we can find some interesting interpretation. For example, here, if we look at the gradient of the loss function with respect to a particular Wj, we can see that this part says the difference between our prediction and the actual label, which means that if our prediction is very far, is very wrong from the actual label, then the gradient becomes large as well, right? Because here you can see that if the difference is large, then obviously that value is also large. And then times the value of the jth feature as well. So I'm thinking of this as kind of a scaling purpose. So if the feature itself is big, let's say 1 million or 10,000 millions or so on, then of course the gradient should be adjusted to that scale. But if this feature is kind of a small value, 0.1 and so on, then the gradient will be scaled to becomes smaller as well. Okay, so the gradient here consists of two types. First is how far we are from the actual label. And then second, the feature itself, is it large or it is small? Is it small? And then we'll multiply these two values and it becomes the gradient of the loss function with a particular Wj. For me, I think this part is the most interesting, which means that if our prediction is very wrong, then the gradient will become large, which means that our W will be pushed or will be shifted with a large value because our current prediction is very wrong. Okay, but if our current prediction is already very good, the difference with the actual label is already very small. It means that we will improve our W with also a very small value because our current W is already good enough. It can make a good prediction. So in other words, do not change too much of our W. Okay, so if our prediction is still very wrong, then change the W with a large value. Change it quite drastically. If our prediction is already almost correct, then do not change our W that much. Okay, so that is the interpretation of the gradient. Now let's take a look at an example. Suppose we have an object with two features and then the first feature is 1, the second feature is 2 here, and then the label is 1, and then At some point, this is the W and the beta that we have. So W is for the first feature, W1 for the first feature, W2 for the second feature, and the bias term is 0. Eta is 0.1. This is a small constant. What I'm asking in this example is that perform a single update step using this formula. So update the W1, W2, and B using this formula. Remember that this means the old W, this is the constant, and this is the gradients of the loss function with respect to a particular W. So if we look at the formula here, first we need to have this gradient to update the W that we would like to update, right? And then from the previous slide, we have seen that the gradient of the loss function with respect to a particular weight looks like this. So it is sigma wx plus b minus y times xj. Okay, so here's the gradient. And then let's plug in the number. Wx plus b. So w1 times x1 plus w times x2 plus b. So here's 0 times 3, 0 times 2 plus 0 because b is 0 equals 0. So this takes care of the wx plus b part. Okay. And next we plug it into the sigmoid function, which looks like this: 1 over 1 plus e to the minus of this value, wx plus b. So 1 over 1 plus e to the power of 0 equals 1 over 2. So we have done this. And then y is already known from the problem, y equals 1. So just plug in y here. 1 half minus 1 is minus 1 over 2. So we have taken care of this part. This is minus 1 over 2. And then it depends on which W that we would like to update. For example, if we'd like to update W1, then we multiply the last value with X1, right? Because we're updating W1, so this is X1. So multiply this with 3. It becomes minus 3 over 2. But then if we want to multiply it with, if we like to update it with respect to W2, and then we plug in X2 there. Okay, so we get, this is the gradient of the loss function with respect to W2. And then finally, to update the B, we take the gradient with respect to B, and then for B, we do not need to multiply this by anything, so the result is just minus 1 over 2. So these three are the gradients for each parameters that we would like to update. So up to this step, we have got the gradient of the loss function with respect to W1, with respect to W2, and then with respect to B. And then we put them in the vector of gradients. Okay. Once we have all the gradients, then we may perform the update for each parameters. Okay, it simply says first take the old value for each parameters. So in this vector, you can replace W1 with 0 because this is the value here, the old parameter. W2 replace it with also 0, and then B replace it with 0. So this vector is 0, 0, 0. Minus eta, eta you use 0.1, and then this is so W, the old W, eta, and this is the gradient. So you plug in the vector of gradients to there. Okay. So for the first one is 0 minus, so let me write it down. So the first row, W1 is 0, eta is 0.1, and then the gradient with respect to W1 is minus 1.5. So you see the final result is positive 0.15. So these vectors show the new W1 is 0.15, the new W2 is 0.1, and the new B or the bias term is 0.05. So that's one iteration of updating the W and the bias term using gradient descent. So let's make an interpretation about why the weights that we start from 0, and it is updated to become more positive, 0.15, 0.1, and 0.5. We're starting from looking at the current model's prediction. Using these weights and the bias term, our current model prediction, which can be calculated from sigma of Wx plus B, is 0.5. But the actual label of that instance is 1. So our prediction is just zero point 0.5. The actual label is 1. So we need to somehow push the weight such that our prediction will be closer to 1. So that is the meaning of performing gradient descent. We're shifting the weights and the bias terms such that our prediction would be closer to the actual label of the instance. Okay, so that's why we have the new W1, W2, and B. And then if we use this new weights and bias term to make the new prediction for the same instance, the result would be 0.668. You see that with the new weights and bias term, this is closer to the actual label, which is 1. And then we will keep performing this steps, the gradient descent steps, such that the weights and the bias term are keep updated such that the result will be closer and closer to the actual label of the data instance. Okay, so now you have learned the complete logistic regression, starting from how to use it, and then how to measure the loss, and then finally how to perform gradient descent to keep improving the weights and the bias term. In the next video, I'm going to show you the details about the deriving the gradient of the loss function with respect to the weights and the bias term. Okay, thank you and see you on the next video.